For the first task, the idea is to recreate the Jobac method, which is effectively a linear regression on functional groups of molecules. So you are provided with this text file, which contains the enthalpy information in the first column, and then the presence or not presence of other groups in the remaining 41 columns. Now the file can be read directly with NumPy using NumPy load.txt, which is able to fetch the data from the web. And now we need to select this down to the first column and the remaining columns. So that's what A and B are doing in this case. So what we have is the selector in brackets, where we first select all rows and then we select just the first column. This is for B, the enthalpies information. And then we select the column A, or the matrix A, which contains all rows, but then only the first and all following columns. Now we have split this in two, where A is actually the coefficient matrix, and B is the property vector. Now, in a regular, if A were a square, which it isn't, but if it were a square, you could just directly invert that. Now, A is not square, so what we need to do is we need to use the pseudo-inverse as demonstrated in the lecture. So what you do is you calculate the inverse of A using the pin function of NumPy. With this, we can now calculate the coefficient vectors, so what each and every functional group in the Jobac context contributes to the total enthalpy of formation. We do that by calculating the dot product between the inverse of A and the property matrix B. That's equivalent to a regular least squares regression. Now we have the property vector X, and with this we can calculate what would be the prediction of the individual feature coefficients. So we do that by calculating again the dot product, but this time between A and those coefficients, meaning that for every row in A, for every molecule, we now get a prediction based on the regression model. We can compare this to the corresponding values in B, because we know that B is the calculated one, the true one, and we want to know how far off are we. That's why we calculate the absolute value thereof, such that the sign doesn't matter, and then on the NumPy array you can always call .mean in order to get the average of all entries in that array. If we now divide this by the mean of the enthalpies of formation that we like to explain, then we see that our linear regression is pretty good. We are off by 0.5% only in terms of explaining the variance of this particular, explaining the mean of this particular quantity. Now for the task 2, the idea was to follow largely the procedure outlined in the lecture and give you some hands-on experience on how to do vibration frequency calculations on your own. So what we do is you get the molecule definition, and then you have this geometry already provided. So what you do is you run a Hartree-Fock calculation first, then you calculate the Hessian thereof, and both of these steps are going to take just a little while. Then we can rearrange the Hessian in order to be in the form that we would like it to have for the later calculations, and not 4-dimensional but rather 2-dimensional. We mass weight this by the corresponding lists of the corresponding element mass, and then we can use the M-half matrix in order to get the weighted Hessian. Note that this is not a matrix operation, this is an element-wise multiplication within those arrays. Based on this, we can then calculate the eigenvectors and eigenvalues with this eigh function, which you can use because the weighted Hessian is square, so it doesn't have to be the eig, the more general function. And after changing the units, we now get all those frequencies. Keep in mind that these frequencies now contain 6 of the lowest ones, which are just the 3 translational and 3 rotational degrees of freedom, hence are close to 0, or at least very small. And the task was to give the difference between the second and third. So we look at the one with index 7 and the one with index 8, and we get our difference in frequencies of 2 to 4.37 wave numbers.